Okay, hello everybody, and welcome to the first gravity seminar of this semester. Today it's a great pleasure to have Alessandra Buonanno from the Max Planck Institute for Gravitational Physics in Potsdam. She will be telling us about advances and challenges in modeling gravitational waves from binary black holes. Please, Alessandra.
Okay, so first of all, thank you for giving me the opportunity to give a seminar here on gravitational waves. So I want to start with the motivation and the outline of this presentation. So as you know, maybe I have to do okay with the recording. Gravitational waves have become a groundbreaking tool to explore the universe. And in order to extract information on astrophysics, on cosmology, detecting possible deviations from general relativity, and discriminating them from other effects that could be very tiny, like effect due to the environment where the binary is, or cosmological effects, for example, gravitational lensing. We really need very accurate predictions for the two-body dynamics and the gravitational radiation. So until now, the searches with LIGO, Virgo, and Quagga have been using template banks with waveform models that describe a binary system on quasi-circular orbits. And this is also true for the inference analysis, Bayesian analysis that are done once a signal is discovered. And the reason why for many years one has focused on quasi-circular is because there was the expectation that the majority of the signals would come from a scenario in which the binary always existed, originally with stars that then collapsed to black holes, to neutron stars. So seeing eccentric binaries would be considered like a subpopulation. So I will describe in this talk the extension of a first attempt to extend the waveform to eccentricity, although for the moment, not in the full generic case, because we still keep the spin of the black holes not to be generic, be precessing, but align with the direction perpendicular to the orbital plane. And I will show you results of an inference study that used 57 of the gravitational wave signals that were discovered in the first 3 runs of the LIGO and Virgo Quagga collaboration. Then I will also present a comprehensive study to understand the accuracy of the current waveform model, the quasi-circular orbit one, which are our state-of-the-art waveforms, in particular when we try to use them for more sensitive detector or upcoming runs, which use the same facilities or future detectors on the ground and in space. And I will focus on some scientific cases that can be affected by the fact that the waveforms are not very accurate. So I'm pretty sure all of you, or a big portion of you, have seen this plot before. This is the stellar graveyard that represent the different black holes that have been discovered by the LIGO and Virgo collaboration. Although I have to highlight that there have been also tens of events that have been pulled out from the public data with independent analysis. And in blue, you see the black holes. So you have 2 black holes that then merge with each other and form a black hole with a larger mass. And the spread in the mass of the black holes is quite interesting. It's more or less between 5 solar masses and 100. And this has to be contrasted with the black hole that we see in our galaxy through X-ray. They are in binary systems, which have clearly a lower mass. In orange, in this plot, you see the neutron stars, and in form of, you have 2 neutron stars that merge with each other and form more likely a black hole or a neutron star black hole system. Unfortunately, I don't know why at this moment my mouse doesn't work here. And in orange, you see the distribution of the mass of the neutron stars seen as pulsars in our galaxy. So I want to highlight already in this slide one of the, actually the first event that was published as part of the ongoing run of the LIGO Virgo Quagga collaboration, was a neutron star black hole system. I will come back to this later, which was discovered the 29th of May 2023, just 1 year ago. We denote the events like the year 23 and then the month and the day. And these are some peculiarities, as I said, I will describe later. So the detectors have been operating in the last 9 years, and you can see here the evolution in time. And what you see also is the numbers, 80 megaparsec, 100, etc., that represent the maximum distance at which we can see a binary neutron star. And the fact that it's increasing over time means that the detectors are becoming more and more sensitive. So we are at the 4th run, which started a year ago in May. And for almost 10 months, it operated only the 2 LIGO detectors. But at the beginning of April, Virgo also joined the network. And until now, 96 candidate signals have been observed by LIGO Virgo, plus the event I was highlighting before. I can talk about these numbers because we have public alerts, and so everybody actually can connect to a web page and see that the events that have been, the candidate signals that have been discovered so far. This ongoing run will end sometime at the beginning of 2025. There will be a gap of 2 years, more or less. And then the last run, which is called 05, which will be a design sensitivity for the detectors, will operate until the end of this decade. Toward the end, we expect also the LIGO India detector operating. And at the beginning of the next decade, there will be also some upgrades of this detector already existing, some upgrades to make them even more sensitive that go under the name of A-sharp and Virgo Next. But overall, until the beginning of the next decade, this detector will be able to probe more or less our local universe for binary black hole, neutron star black hole, and binary neutron stars up to a redshift of 1, 2. I will come back later in my presentation to what happens actually in the next decade. Okay, so a few words. So we detect the waveform with interferometers, and we monitor the differential mode of motion of the mirrors that hang by wire at the extremity of Fabry-Perot cavities, as you can see here, with extreme precision in order to measure the strain, which is basically the amplitude of the wave at this with very, very, very tiny, 10 to the minus 21, for an object which is actually at like the Virgo cluster, like a binary neutron star. Now, for this talk, what is important is also how we detect the signals from binary systems. And we use the best way of doing it is using match filtering or signal processing. So basically, I show here now in a small animation. In the lower panel, we have the data in black. We slide or correlate the data with a template that we produce in advance. And we will discuss this in a moment. We build this correlation where we maximize on the parameter of the binary. I'll show you again. And when this correlation, which is shown in the upper panel, becomes larger than a certain threshold that we have set, knowing the noise in the detector, we can claim a detection. Of course, the process is more complicated than what I'm just showing here. The point I want to make is that in order to detect the signals, we need a bank of templates, and we need many of them. And even more of the order of millions of waveform models we need for inference analysis that happen after the detection. So why we are interested in the waves is because they carry information about the source that has emitted them. So let's look a moment in a more qualitative way how the parameters in the binary are imprinted in a waveform. So this is a typical waveform with the spiral part, and then at the end, you see the frequencies increasing, then you have the merger, and then in this case, the 2 black holes form a new black hole, and the black hole rings the space-time. And from the frequency evolution, we infer the masses. From the amplitude and the masses, we can infer the distance where the binary was with respect to the Earth. from the time of arrival, the amplitude and phase at the detector, because we have at least 3 detectors, the 2 LIGO and Virgo. CAG has been also operating, although not at the same sensitivity, and for shorter amount of time, we can infer actually the sky location. Moreover, the waveform at the top is of 2 objects going around each other on a quasi-circular orbit, while the waveform here on the left has more features, because this could represent either the case in which the binary moves on an eccentric orbit instead of quasi-circular, and the spin of the black hole, so the neutron star, are actually precessing around the direction of the orbital angular with respect to the direction of the orbital angular momentum, and so you see this kind of modulations in the signal. If you were comparing a waveform for a binary black hole and a binary neutron star, having the same parameter, the same masses, for example, they would become more and more different toward merger. Of course, the merger will be very different because in the case of the neutron star, you have matter. So what happens after the 2 objects merge is very different from what happens when you have 2 black holes. But notice that even before the merger, as you see from the waveform on the right, you have some dephasing between them. And this is because the neutron star has a parameter which is not there for black holes. It's called the tidal deformability parameter. It actually describes the tidal deformation of the neutron star due to the tidal field of the companion. And they can be there, and by measuring this kind of dephasing, we can learn about the composition of the neutron star. Finally, we can compare the waveform with deviation from general relativity, with theory that deviate from general relativity, and we can probe the theory of gravity, see general relativity or something else. So now, from these few slides, I hope I convey the point that so we need to know this waveform very accurately, and in particular, if we think also of match filtering or also the Bayesian analysis that we do later, we need to know in particular the phase of the waveform very accurately over time. And I want to, in a slide, try to explain how actually we can get this phase. So perhaps you have learned that the strain of the gravitational wave, the gravitational waveform, is proportional to the derivative of the quadruple moment of the source, the second time derivative of the quadruple moment of the source that has emitted them. So if you take a binary with 2 masses, M1 and M2, you can introduce the reduced mass and the symmetric mass ratio, which is the reduced mass divided by the total mass, as you see on the right. And the symmetric mass ratio ranges between 0 when one body is much bigger than the other, and 1/4 when the 2 bodies are comparable. So you can do your calculation for a quadrupole, 2 objects going around each other on a quasi-circular orbit. You can introduce this parameter V, which is basically a velocity that you express in terms of the orbital frequency, just using the Kepler law. And you get the waveform on the left, which is proportional to this asymmetry, the symmetric mass ratio. It depends on the total mass, inversely proportional to the distance d. And it scales as v over c to a power 2, which is actually comes from the 2 derivatives of the quadrupole. And then you have this cosine of twice the orbital phase. This also is a consequence of the dipole. And how do we get this phase? So this is what we want to get very accurately. Well, if you think about the in-spiral, what we do is that on one side, you can compute the binding energy of the system, which at leading order is just given by Newtonian gravity, by the formula I wrote there, minus mu divided by 2v squared. Then you can compute the luminosity, how much of energy is radiated at infinity. And the leading order term in an expansion in the velocity is given by this formula here. It's a famous formula, sometimes it's called also the quadrupole formula. Not for binary, but in the generic case, was actually obtained by Einstein in his paper of 1918. And then you put together these 2 expressions by saying, well, there is an energy balance equation. The variation of the energy is given by the derivative of the energy to the is equal to minus the flux at infinity. And if you are considering a circular orbit, then you can rewrite this equation as an equation for omega dot, the orbital frequency. And then just you integrate the omega dot twice, and you get the phase. So of course, this is approximate because we cannot just use the leading order term in an expansion in V. Also, this applies in the case you have the in-spiral, then at some point the two objects merge with each other, so something has to happen. But just to give you an idea, the idea that you need to know very well two things: the two-body dynamics on one side, so the binding energy, and the dissipation, how much flux is emitted by the system. So let's look a little bit more in detail. So we have to solve to get this waveform, the Einstein equations, which I wrote here in full glory. And the best way of solving this equation is to do it numerically on supercomputers. But this is very slow. It's slow because, for example, to produce just the two black holes going around each other for 15 orbits, it takes 1 month or 3 weeks, depending on the parameters of the black holes, the spin, and the mass ratio. So numerical relativity basically can be used in a regional parameter space where the separation is not very large, and also the mass ratio is not very large. Then we have other ways to solve the Einstein equation, and this is more in a perturbative way. You have a small parameter that you use in the expansion. So the oldest one is the so-called post-Newtonian theory, where you expand the Einstein equation in powers of V over C, which, because of the viral theorem, is also related to the strength GM over RC squared. And this is a good approximation for large separation and slow motion. So post-Newtonian theory is somewhere here. In the last few years has become quite, has had some success, this post-Minkowskian approximation, where you expand the Einstein equation and the radiation in powers of the Newton constant G. So basically you don't expand in the velocity. And so this also could represent, for example, scattering or large eccentricity. You can expand the Einstein equation in powers of the mass ratio. So you don't expand in velocity of the strength. So this means it's completely strong field. But you can apply this only when you have a very large body and the companion is very small. Then we put together these approaches, this method in a theory which is called the effective one-body theory, which can combine them and also as an ansatz for the merging down, but needs to be then calibrated to numerical relativity. And I will tell you a few, I have a few slides about that. And then another way in which we build the waveform models, because with the effective one-body theory, we build a waveform in time domain. So we have to solve some equation. I will show you in a moment. But the phenomenological ones, they are very convenient in terms of efficiency because they are in frequency domain and they use expressions which are in closed form. So you can basically generate them very fastly. And they are built by fitting together effective one-body, post-Newtonian, and numerical relativity.
Alessandra?
Yes, equation.
Can I ask a question? So what are the observational prospects for measuring waveforms of like scattering waveforms that you said are relevant for the post-Minkowskian approximation?
Yeah, well, the scattering, I think it's, you know, I mean, I have seen some papers that have made some predictions and it's really not very likely. However, I mean, people, more than scattering, you can have a dynamical capture. So, you know, two bodies come very far from each other and then they approach each other because of the dissipation, you know, of gravitational waves, they can be captured. And that's also quite rare. But you could have highly eccentric binary systems. We are not observing, at the moment, we don't think we are observing them, but it could be a subpopulation. And we expect that increasing the number of events, we will actually at some point, maybe, you know, I will show you later, the rate of eccentric versus quasi-circular is 1%.
And then these highly eccentric orbits can be approximated by scattering orbits in the relevant regime where they fly by each other and
yeah, actually, so I was not planning to discuss this much, but the main use of this post-Minkowskian that I mentioned here is the fact that you do calculation for the scattering case, but then you can actually map the scattering to the scattering result to an Hamiltonian, and then you use the Hamiltonian for generic orbit, including also bound orbits, but they can be highly eccentric. So you use the results in that way, not because you are expecting to actually see these, scattering orbits, but you are using the results of calculation in that regime to learn about generic orbits.
I see, thanks.
Okay, thank you for the question. You can ask question also, of course, during the presentation. So a few slides about this effective one-body. What this effective one-body does is, so instead of using results in perturbative expanded way, we should actually include in our calculations, whatever we know, which is known exactly or in a non-perturbative way. And an example I want to make here is that, for example, the Hamiltonian of the two-body system, we know it exactly in the test body limit for Schwarzschild, for a body moving in the geometry of Schwarzschild or Kerr. And so we can do this post-Newtonian expansion around the solution that we know at all orders in the test body limit. And so this method provides a mapping between the two-body description and the one-body one, which describe the motion of an effective body in a deformed black hole spacetime, as I wrote here, where the deformation parameter now is the mass ratio. If the mass ratio is 0, the symmetric mass ratio, you recover Schwarzschild or Kerr. And what this method provides is a new Hamiltonian, which is resum with respect to the Hamiltonian of the deformed black hole spacetime. And just to give you an example, suppose that the spin are 0, so we are in Schwarzschild, and you can actually derive the Hamiltonian in the effective description from the Hamilton-Jacobi formula equation. And this is the effective Hamiltonian. This potential here, so you see you have PR here, R, and the angular momentum. And this potential A and B, if you remember the spacetime of Schwarzschild, this potential where U is M over R, if you neglect the correction in the mass ratio, nu is actually 1 minus 2m over r. So you recover basically the potential of Schwarzschild, and the same thing will happen for this potential here. This is actually going to be 0. But what this method does is now adds these post-Newtonian corrections that are powers in Gm over r with correction that depend on nu, a different post-Newtonian order, and today we know this order up to 4pn. But you can add higher order corrections that are unknown today that you then calibrate to numerical relativity. So if you plot actually this potential divided by r squared, for Schwarzschild, the peak of this quantity here is the light ring, right? Is the light ring. And this plot is just showing you basically how this potential divided by r squared varies when you change the mass ratio of the binary very smoothly. Okay, so what do you do with this Hamiltonian? Well, you can write Hamilton equations, and now you have to add a radiation reaction force, and this radiation reaction force has to be also resummed based on post-Newtonian theory. I will not go into the details here, but then you evolve this Hamilton equation with dissipation, and then you have also the modes of the waveform that you have to resum from post-Newtonian theory. So I plot here just the tutu mode, for example. This is the evolution of the gravitational wave frequency that increases over time. And then at some point, you form a black hole and the frequency flattens to the least damp quasi-normal mode. So how we complete the waveform in this method? In the 70s was pointed out that close to the so-called light ring, the quasi-normal mode are triggered. And so we add a superposition of quasi-normal modes to complete the waveform, okay? And we use a function, which I wrote here for the mergering down for the different modes, which has an amplitude that depends on time and a phase that depends on time. And this is a superposition, just one for the moment here, of quasi-normal mode, where the real and imaginary part are predicted from GR for a black hole with a certain mass and spin. Now, the full waveform is built by arriving to the end here, T match, and then completing it with these ansatz for the mergering down. All the quantity in Sion, for example, the point at which we do this matching, these parameters, the parameters I introduced before, we all calibrate to numerical relativity. So how do we do this calibration? Just in one slide, actually one plot. So we start with the effective one-body waveform, which is not calibrated to numerical relativity, that I show here in red. We compare with the numerical relativity, you see that at very earlier time, the two agree with each other, so more in the low frequency regime at large separation, and then they start dephasing. And we want to correct that dephasing with these calibration parameters. So we tune them to numerical relativity until they match very well, which is what you see at the end of the process. And we repeat this for many, many numerical relativity waveforms at our disposal. So this calibration was done with 441 numerical relativity waveform with spin that are aligned or anti-aligned with the orbital angular momentum. This was done to calibrate the most recent SUBNR, which means spinning effective body calibrated to numerical relativity. We are at the 5th generation, that's why V5. And this plot shows the distribution of the numerical relativity waveform in the mass ratio and a combination of the spin of the binary. And the different color represent different mass ratios. So this is work of several postdocs and graduate students in our group here. And these waveforms then are used in the template bank. For example, this is a projection in the template bank of the masses. At low masses, just we use plain post-Newtonian templates because we don't care about the merger, since the merger is at very high frequency for a binary neutron star. But for neutron star black hole and black hole, we have to use a waveform which include the merger. This is the way in which they are calibrated. So I want to mention, because I will also comment about them later on. So as I already mentioned, there is another family of waveform model called phenomenologica. There is, which is used by the LIGO and Virgo Kaga collaboration. There is another family of effective one-body waveform that is called TOB-RISAM-S. And finally, there are also waveforms that have been produced in the last few years, interpolating directly the numerical relativity waveform where they are available. Unfortunately, we don't have them everywhere in the parameter space, but where they are available, these surrogate models of numerical relativity are, of course, the best, more accurate waveform at our disposal. Okay, so let me show only one result of the gravitational wave observations. The most recent one, discovered the 29th of May 2023. And this it's a mysterious object because it's a mysterious binary because the primary object has a mass in what is called the lower mass gap. So what is that? So in this plot here, unfortunately, my mouse doesn't work for this slide. So the black region represents the region of masses between 3 and 5 solar masses. And based on observation of black holes as in X-ray in our galaxy, we are not observing black holes in this region. So there was then the assumption that black holes will not, from the collapse of star, will not be produced in that region for some reason. But the primary mass of 230529, as you can see, it's really certainly below 5 solar masses. And the uncertainty goes up to 2.5 solar masses. There are also other objects that were observed during the third run of the LIGO and Virgo collaboration, which have, for example, the secondary mass of 190814, also below 3 solar masses. And interestingly, this region of low, total solar masses is also a region where recently a binary pulsar, one of the companion in the binary pulsar, was discovered to have a mass which is too large, perhaps, to be the mass of a neutron star, and perhaps too small to be the mass of a black hole. So we are starting populating a region which is a bit in the border between neutron star and black holes. So GW 230529 was analyzed with the two IMR phenom X and SUBNR V5. This is actually a simulation that Tim Dietrich did of the event. And you can see at the very end, the neutron star is disrupted by the black hole. At the top here, you see the masses of the object. I was saying, actually, this event is quite interesting because as you can see, if this is a neutron star black hole, the mass ratio is not very large. and there is more probability that the neutron star is disrupted before plunging, and so you can actually create an accretion disk around and maybe trigger an electromagnetic counterpart. Although in this case was not observed, and even in this simulation, there is no much disk, around the black hole that forms. So these two waveform models that were used to the analysis are reported, the position distribution are reported here, putting together the results of them for the masses of the two events. And here it lies GW 230529 is this region here, contrasted with other neutron star black holes that have been observed, and the two neutron stars that have been observed during O2 and O3. One thing I want to stress is that so the only way for this event that we concluded one of the two objects is a neutron star is basically the range in the mass, which is below more or less 2 solar masses, because we couldn't constrain the tidal deformability parameter, because this is an event with quite a low signal-to-noise ratio. So we cannot say much about the tidal deformations. In fact, the waveform that we use for this plot are actually waveform for binary black holes. For this event, systematics due to waveform are negligible, so we should, trust the results here. And I wanted just to say what could be the origin of this primary mysterious object. It could come from the core collapse of a supernova with substantial fallback that increase, the mass of it. And making it, larger than 2.6 solar masses. It could be the accretion on a neutron star. Could be the merger, so a black hole that had such a small mass because came from an original merger of two neutron stars, and then form a binary later with a black hole. With a neutron star. Or it could be a primordial black hole. So already a few papers have been written about that. Okay, so now that I presented some of the results, at least the latest one from the collaboration, I want to enter more in the second part of my presentation, unless you have any question on this first part. Okay, if not, I then continue. So now the first question is, we are using this waveform model for, in particular for the follow-up analysis with precession and higher modes and precession of the spins. Are they accurate? How do we establish whether they are accurate enough? So we can compute this quantity that is called the mismatch, which is 1 minus the maximum on the time and the phase shifts, that time and phase that you can apply of the overlap between the model and, for example, the numerical relativity waveform, which is our best representation of the signal. And the overlap is given by the formula you see there in frequency domain, where you multiply in frequency domain the model and the numerical relativity waveform, and you divide by the noise spectral density of the detector. The overlap is also normalized so that basically when the mismatch is 0 means that you have complete agreement between the model and numerical relativity. So we computed in this paper led by postdoc Tony Ramos Boades this mismatch between 1543 numerical relativity waveform from the XX collaboration, which are with a spin that precise, as I said, and these two models, the two state-of-the-art models used by the collaboration, although IMR Phenom X has been also recently improved, as you can see from the papers on the bottom. So this is the maximum mismatch average on the signal-to-noise ratio, and also maximize on the mass of the binary between 10 solar masses and 300. And what you can see is that the IMR Phenom, although is more efficient it's fast to produce waveform because it's in closed form in frequency domain. By producing something which is very fast, you also lose some accuracy. And so you can see that there is a tail going up to, more than a few percent, up to 10%. So where this numerical simulation lies, so this plot on the right shows chi effective, which is a combination of the spin in the binary versus the mass ratio, and with all the dots representing numerical relativity simulations. The one in green and yellow are the precessing one, And you can see the precessing, the 1443 are all, there are many, but they are all in the region up to mass ratio 4 and spin maybe 0.6, 0.7. The blue are all aligned spin or anti-aligned spin. And they go to larger mass ratio, which is interesting, but they are not covering very well the parameter space. There are very, empty regions. By the way, the color here represent this parameter chi-p, which measure basically the precession of the spin. So it's a quantity that tells you how much the spin, how much spin there is on the orbital plane. Okay, so another way of representing these results is now to plot this mismatch for different value of the total mass of the binary, as you can see here. And what you see again, these are the violin plots that for IMR phenom X, the median, which is represented by the horizontal small dash, small line in the middle of the violin, increases as you increase the total mass, so they become less accurate at, toward the merger. And also they have these tails, as you can see. Now, this is comparing to numerical relativity, but unfortunately, I mean, as I was showing you in the previous plot, there are many regions in the parameter space where we use these waveform models, but we don't have numerical relativity against which we can assess the error. And so what we do also is to compare the model with each other. And this is shown in these two plots in the bottom. So the color represent the mismatch. And so as they become, as the mismatch becomes yellow, the models differ from each other more and more. And not surprisingly, this happens in the corners where Q, the mass ratio, is large, and the chi-p parameter, so the precession of the spin, is large. Okay, but I wanted to give you an idea, what does it mean that the mismatch, for example, is 12% or 2%? So let's make an exercise. So we inject a numerical relativity waveform into the data, and we recover with these two models. In one case, the disagreement is 12%, and the other is 2%. And we consider a waveform that has a signal-to-noise ratio of 20 for O5, which is the upcoming run. So on the left, you have the posterior distribution for the masses. So again, NR is injected. In the green is the recovery with the model, which has 2% of disagreement, and orange is the one that has 12%. And you can see that the one with 12% recovers the primary mass, so does not recover the primary mass, is outside the 90% credible region. And actually, this is even more serious, the problem, if you look at the spin recovery. So chi-p, as I was telling you, is the parameter that tells you, where is the, how much precession there is. So the signal, the true parameters are in the intersection of the two lines, the black lines. And the model with 12% of difference would say that basically the system was not highly precessing. But on the other hand, the other model, which has only 2%, says that the system is highly precessing. And having a bias of this amount is really not good because one of the ways of discriminating different channels, whether these come from dynamical capture or isolated binaries, is actually the presence of precession of the spins. Okay, but besides the accuracy, the important new challenge is the inclusion of eccentricity. So this is a visualization, actually is the flux that is emitted by the binary, and it's an eccentric binary, originally with eccentricity 0.3 at the beginning. The eccentricity is reduced over time. And there is the primary spin is precessing, so the orbital plane is actually changing. And in fact, maybe this is difficult to see immediately. I will rerun again a moment. Sorry, 1 second. Because what you can see is that the majority of the flux is actually perpendicular to the orbital plane, but the orbital plane is precessing, and so the blobs are also changing. This is what you see. In the bottom, you have the gravitational waveform, which now you see how complicated it is, much more than the kind of waveform I was showing you before. And this is due to the presence of eccentricity. So what has been done until now, so we added actually eccentric effect in the radiation reaction force and modes in the effective one-body model. And so there are now a few waveform models that exist within the effective one-body formalism, but only when the spin are aligned or anti-aligned with the orbital angular momentum. So the full case with precession of the spin is not yet available. But let me show you the results using this model. So this is just a plot that shows, again, if you have eccentricity, how complicated are the waveform going toward merger. The different panels correspond to different modes, and all the modes, can be excited in presence of eccentricity. The model can also represent a situation where you have dynamical capture that we just discussed before, which is represented by the orbit on the right plot. And then in the different panels, you have the different harmonics. But now when you compare this model, which is called SUBNR V4 eccentric higher harmonics, which has aligned spins with numerical relativity, this is the plot we obtained. So with respect to the 2000 waveform for quasi-circular that we have at our disposal in numerical relativity, we have only 28 numerical relativity waveform, public waveform from the SXX collaboration. And although the mismatch is not bad, it's below 1%, this is not enough to assess how accurate is this model. Nevertheless, we use this model to analyze several events, and in particular, the event that was discovered the 21st of May 2019. This was the event with the largest black holes until now. And the reason why this event caused actually quite many papers have been written, because as you can see from this visualization, the event, because of the large masses, is very short. And when the waveform model were used to analyze this event, you can see here the posterior distribution for the three main waveform models, the SOBNR, the phenomenological, and the NR surrogate. Although at 90% the posteriors overlap with each other for the masses and the spin parameters, still there is some non-negligible difference. So you see, for an event which is very short in the strong field, the waveforms start to, be not very close to each other. And however, we are not dominated by these systematics, because the 90% are quite broad, because the signal to noise ratio is not very large. And in fact, in the future, what will happen is that the signal to noise ratio will increase. So the statistical error is going to decrease, but the bias is there unless you do something to reduce the bias. So we analyzed this event with the eccentric model for the first time with two eccentric parameters, the eccentricity and the mean anomaly. And I want to focus on the plot on the right, which actually give you the posterior distribution for the eccentricity computed at 5.5 Hertz. The eccentricity varies over time, so you have to set a frequency at which you evaluate it. And you can see that the posterior is completely flat in the region in which we have explored this event, which says that 190521 for us using this model is not eccentric. And the reason why I highlighted this, because there have been papers in the literature saying, on the other hand, that this was not the case, that the event was eccentric. For example, using a different waveform model based still on SUBNR, but with some changes produced by the group in China, Isobel Romero Shaw and collaborators found that this event is eccentric with eccentricity larger than 0.1 at 10 Hertz. And then people working in numerical relativity used numerical relativity waveform against this event and found that this is a binary with eccentricity 0.7. So the story, it's quite, people are not getting the same results. So now, using still this waveform model with eccentricity and spin aligned and aligned with the orbital angular momentum, we use a quite efficient code based on machine learning to analyze many events during the first 3 runs, 57 gravitational wave events. And this is a work led by graduate student Nia Gupta here in our group. So let me say what we found. So first, let me introduce these two acronyms. So we are going to compute the base factors between the model with eccentricity and aligned spins and the model quasi-circular and aligned spin. And we found the following. We found 3 events in this population of 57 gravitational events, which have a base factor larger than 10. And in particular, there is an event which was discovered the 29th of January 2020, which has a log 10 base factor between 1.84 and 475. So why this range? Because this event was affected by a glitch. And depending on the way in which you subtract the glitch, the base factor changes. And changes quite a lot, as you can see there. And this is the range in the eccentricity from that, again, changes depending on the way in which the glitch is subtracted. Now, once you have the base factor, in order to conclude your computation here, you have to multiply the base factor by what people call the Prior's odd. So what is the odd that you observe an eccentric binary with respect to quasi-circular based on our knowledge of astrophysics today? And this was the number 2% that I mentioned before. When you do this multiplication, you end up with the odd ratios, which are between 0.2 and 3.11. So not very strong at the end. But still not negligible, especially if you look at the 3.11 instead of the 0.2, which again changes because of the glitch mitigation. So let me show you now the results in this violin plot. So what is plotted is the eccentricity at 10 Hertz for the different events, the 3 events for which one found a base factor larger than 10. So the first actually on the left is the prior, which is, this is uniform prior on eccentricity. And for each event, the violin plot on the right is when you add higher harmonics in the model, on the left when you only use the 2-2 model. And I was focusing on the event on the middle, which is this 20-01-29. And what is plotted on the top is the base factor, again, when you add higher harmonics or not. So this is, the result that come out from the analysis. Now you can add all the other events, which however we don't see sign of eccentricity. So in this plot, what is plotted is the log 10 of the base factor between the hypothesis eccentric and quasi-circular as a function of the eccentricity at 10 Hertz. And you have the mean, and then what is plotted there is the 90% credible region. So in pink, you see the 1905-21, which is found not symmetric, eccentric. In green are all the other events, which are, have a log 10 base factor below 1. And then you have these 3 events that are represented in blue, in brown, and in orange. Now, when you put together all the results that we obtained from the analysis, the inference analysis, and you use the hypothesis that this is an eccentric aligned spin event, you find that, so if you neglect precession, that the probability of 1 out of the 57 events being eccentric is actually greater than 99.5%. And this number is obtained using actually the base factor, which is the lowest, so the most conservative result. Okay, so I have here 2 slides, but I will not discuss them unless you ask me a question later. I want to go to, in the last, I think I have 7 minutes, Shahar, or something like that. I want to discuss the accuracy.
Yep.
Yeah. Okay, and
even more if you need it.
Okay, and if you have any question, because now I finished the part of the eccentricity, if you have any question, you're very welcome to ask a question. Okay.
Yes, sorry, Alessandra.
Yes, please.
I am Jonathan from the Weizmann Institute. So just to ask, did you do similar comparison between eccentric waveforms with aligned spin and precessing waveforms?
Yeah,
with no eccentricity.
Yes, very good. Thank you for the question. I want to show this slide in particular at the bottom. Okay. So indeed, in the paper, we did, so as you know, or maybe I don't know if you know, so as I was saying before, we don't have a model with eccentricity and precession, but we have model quasi-circular and spin precessing. So what we have done in the paper is that we have computed also the base factor between eccentric aligned spin and quasi-circular precessing. And we did it with two waveform models. One is SUBNRV4 precessing, quasi-circular, and the other is NR surrogate. And for both cases, there is a table in the paper that shows that the hypothesis of eccentric align spin is always favored. This is what we find. Even, I mean, with variation depending on the glitch mitigation, but it's typically favored. And now, however, these comparisons are not, especially with NR surrogate, is not completely fair because the model is different. It's not even the same model. If you go in the limit of quasi-circular, the NR surrogate is not SUBNRV4. So we have done this, as I said, but we have not concluded that the precessing quasi-circular is favored. And I want to highlight here at the bottom of this page that in fact this event, 2001-29, a few years ago, was claimed to be the first spin precessing LIGO-Virgo signal by a paper by Mark Anam and collaborators. However, then it was realized in another paper by Ethan Payne and collaborators that because of the glitch, even the spin precession, cannot be really claimed. I mean, you can have results that change quite a lot. So I think we have to wait for a more convincing event to conclude that either is spin precessing or eccentric.
Okay.
Did I address your question?
Yes, thank you very much.
Thank you. Okay, so let me go now to the part in which I want to discuss the future and also the problems of the accuracy. So we will have new detectors. Well, we hope that there will be new detectors, new facilities in the next decade, Einstein Telescope and Cosmic Explorer. And the sensitivity will, the noise spectral density will increase, will decrease by 1 or 2 orders of magnitude, depending on the frequency range. And in particular, notice the big improvement at low frequency, around 10 Hertz, a few Hertz. And this will bring in band black holes with mass of 1,000 solar masses that today we don't see because they merge outside the bandwidth at too low frequency. And the plot on the right is showing you, in fact, the fact that we can reach this high mass object, and also the large, the redshift at which we can see this object that can be larger than 10. Now, there have been several studies, and it's quite overwhelming to think about the number of events that we will have in 1 year. Only look at event larger, with a signal-to-noise ratio larger than 100, which is an order of magnitude more than what we have today with LIGO and Virgo. We will have 10,000 of binary black holes and of almost 400 binary neutron star, which will be really great to nail down the composition of the neutron star. The signals are going to be also more complicated because there is a new class if these intermediate mass, black holes, mass black holes exist of 1,000 solar masses. They will form intermediate mass ratio in spirals with mass ratio of 1,000. And these are two snapshots of the dynamics at 1 Hertz and 10 Hertz. So it can become quite wild. Then in the next decade, there will be a mission in space. So LISA has been adopted as mission by ESA in January. So this is very important news in our field. The launch will take place in 2035. And LISA will open a new bandwidth around 1 millihertz. We'll see objects that we are not seeing on the ground. The merger of, in spiral, a merger of massive black holes, so million solar masses that you can see here, different total masses, the tracks as they span the detector, the tracks of different multiples of extreme mass ratio in spiral, small object going around a big black hole. There will be black holes that, binary black holes that start to sweep in the LISA band, and then after a year or a few months, they will be in the band of the ground-based detector. It will be quite exciting. Now, there are complications with these detectors in space and also on the ground because they will be much more sensitive. So we will see in a moment we need to improve the waveform, but also the data analysis will be much more challenging because especially for LISA, the signals are not going to be transient. They don't last for a second, a fraction of a second, or even a minute. They are always there during the 5 years of the mission, many of them. And we have to basically extract all of these signals at the same time. So this problem goes under the name of global fit, and many people are working on it. So let me now discuss the systematic challenge with these, upcoming runs 05 and then also the new detectors. So let's take, just to explain what the problem is, a source like 190814. This was the source with the puzzling companion, the secondary mass being perhaps a black hole or a neutron star. But now we assume that the object is highly precessing, and so we assume that it's highly precessing, and the mismatch between IMR phenomenon and SUBNR for this event with these parameters is 4%. And I'm considering a signal-to-noise ratio, so I'm putting this binary at a distance that the signal-to-noise ratio is 75, 405, which is the next run, the last run of the current facility. Now, what I want to show you is a plot of the waveforms. So in black, it is a very long waveform. So I'm 60 seconds, the last 60 seconds. In black is the SUBNR V5 waveform with precession and higher harmonics, which I consider as my signal. And I'm trying to match it. The template is IMR phenomenon XPHM. If I use the same parameters, I don't change the parameters, I get the green. And you can see that there is some differences at low frequency, at low early time, in the amplitude, and then in particular for the mergering down. But now what I can do is that I can do a Bayesian analysis where I can match the IMR phenomenon against the SUBNR, and I get the best fit value, the maximum likelihood value. And then I plot the waveform at the maximum likelihood and also 90% around it, which is the brown. And by varying the parameter, of course, I get a better agreement with the signal, which is in green. But I get a better agreement with a consequence that now I get a bias in the parameter. So to achieve that very good match, I have to change the total mass by 3%, the mass ratio by 6%, and also the precessing spin parameter, Chi-P, by 13%. So this is the consequence of the waveform not be very close to each other. Okay, so what we did here, so that's just the beginning. So now we looked at the entire population, an entire population of astrophysical black holes as predicted by the current analysis. So I call it LVK-like. And by the way, this work was led by the postdoc, actually I forgot to say Arnab Dani. And so we took the binary black hole population for the distribution of the primary mass and also the mass ratio. But we wanted to be more generic for the spin magnitude, because from the LVK population, we mainly get that today that the spin is around 0.2 and then it falls to 0. But here we take uniform in spin magnitude and isotropic in spin orientation. Now, because we are considering 10 to the 5 events, we cannot do a Bayesian analysis using Bilby. So we use the linear signal approximation, and we compute the bias using results and formulas derived in this paper by Flanagan and Hughes and Catherine Valisneri. And the statistical error is computed just using the Fisher matrix. And here I'm focused on the XG detector, which means 2 cosmic explorer and 1 Einstein telescope. And what is plotted here in this plot is basically the ratio between the bias and the statistical error. When it becomes larger than 1, which is the dashed horizontal line, we have basically a bias. I mean, we have a problem because there will be a bias in the parameters. And this plot represents the result for the shear mass, the symmetric mass ratio, the primary spin, and the luminosity distance as a function of the SNR. So there is a large part of the population that can be affected by the systematics. And the number you can keep in mind is that, for example, when the primary spin is smaller than 0.4, which is not a very large value, 25% of the population is going to be biased. Okay, but we move away also from the LVK population, because we say, okay, but as the detector become more sensitive, we are going to see more extreme, subpopulation, which will be more interesting. So instead of using the population of the LVK, which is here in brown, we span the entire parameter space up to mass ratio 30. And we allow, in fact, Chi-P and Chi-effective to be much larger than what is predicted by the LVK population. And so I want to show now the results of this more agnostic study. And let me say first one thing. As I was mentioning before, the systematic bias become less important if the binary, as I wrote here, is at larger distance. Why? Because if the binary is at larger distance, the statistical error increases because the SNR is decreasing. And so in the formula, delta theta divided by the other delta theta, that ratio becomes automatically smaller. And so we introduce what we call the bias horizon, which is basically the distance up to which a particular parameter theta is going to be biased. So beyond that distance is no longer to be biased. So let's look at the luminosity distance. And so these plots for the mass ratio chi effective and chi p show the scatter, so the distribution of the 50,000 binaries. The color is the distance to which the luminosity distance is biased. So let me now explain in a moment what does it mean. So if the spin are small, you are in this region here, which has a lot of brown, which is small distance. So small spins means that the biases will be present only at short distance, where the SNR is very large, and maybe it's also unlikely that we are going to see that binary. And this also is true if you go to the low spin precession, right? Low spin precession, the biases are present only at short distance. So actually the green regions are more extreme, large mass ratio, large precession, and they will affect large distances where we still care. And these are the results with A sharp, but you can find in the paper also the results for O5 and the XG detectors. Now, let me go from LVK population, more agnostic population. Now let's consider the golden binaries. So these are the binaries for which that will be associated to very interesting science case. For example, cosmology, recover of the distance and the sky localization to basically get the redshift for a dark siren binary and to get the Hubble-Lemaitre parameter. So on the left, this is a binary, again, like 1908-14, where the mass ratio is around 10, but highly precessing. And this is the signal-to-noise ratio for O5, A sharp, and XG. So what is the result? We inject, again, SUBNRV5, we recover with IMR phenom X. And this is the result for the luminosity distance. The true value, again, is the vertical line. So for this event, O5 and A sharp, still okay, the posterior distribution at 90% encompass the true value, but XG is completely off. We will have a bias in the distance, non-negligible, but you can also appreciate in the inset is actually the sky localization. And you will see that for XG, Einstein Telescope Cosmic Explorer, the posterior distribution is not where the galaxy is, which is where the two horizontal and vertical lines intersect, but is away from it. So that's a problem. But let's consider another case where the mass ratio is 6, but the signal-to-noise ratio, as you can see here, is larger than this event on the left. And this is also actually high spins and precession. And this is really not good because even O5 and A sharp are going to have a posterior distribution away from the true value. And the sky localization is also completely away. So what also you appreciate from these results is that sometimes the posterior distribution for the luminosity distance are on the left or sometimes on the right of the true value. So if you think about putting together, stack many events to get the Hubble-Lemaitre parameter, maybe this effect average, we don't know yet, we want to do some study about that. But the reason why it's sometimes on the left or on the right is because this is a precessing system, and the luminosity distance depends also on the inclination and on the precession at the time in which, the precession at the time in which the binary is actually sweeping in band. And that makes, the bias sometimes positive, sometimes negative. So the last case I wanted to make is, does not concern cosmology, but the neutron star mass and the black hole mass. In the case in which they are at this edge of the lower or higher mass gap. for the pair instability supernova or for this 3-5 solar mass. So again, we take the same example for the masses and spin I had in the previous slide on the left, but now I'm looking at the mass of the secondary and the spin of the secondary. And you can see the mass of the secondary is not recovered at 90% credible interval for all the detectors, although you may notice that the variation in the mass is very small, 2.48 to 2.60, but still, you know, for people looking at the maximum mass of the neutron star, you know, it does matter or will matter in the future. And on the right, I have again the smaller mass ratio object, but larger signal to noise ratio, highly precessing, and I'm looking at the mass of the primary, which is 61.8. And now, if I use the model with precession, the signal with precession, I get posterior distribution, which are the solid one, completely outside the true value. And if I don't put precession, they are still outside the true value, because in this case, the signal to noise ratio are large enough that you are really seeing these biases. Okay, so actually I have 2 slides, but I think I'm completely off the time. Char, what do you tell me? Actually,
yeah, I mean, you can take a few minutes if you want, but
okay, maybe
yeah.
you can ask me if you want to know about the impact on test OGR for Lisa. So I want just to, this is the slide before the last. So how do we tackle this problem? So we have actually a precision challenge that we have to address for the upcoming runs and the next generation of detectors. And we have to basically improve this waveform model by 2 orders of magnitude, but we also have to improve the numerical relativity waveform that we use to calibrate these models. And besides the accuracy, we really need to include all physical effects. So I was talking about generic orbits, eccentricity, but the binary could be in accretion disk, for example, and in that case, so we have to take into account the interaction with the environment. There have been some papers about that. Of course, going beyond general relativity or new physics, another effect that has been pointed out also in the last few years, in this particular picture refers to a source for Lisa, gravitational lensing. So if the wave pass through, for example, a galaxy in this example, depending on the mass, actually in the plot on the left, but depending on the mass of the lens, you have example A, B, and C, the lens waveform in black, and you can see how much the waveform colored can vary depending on the mass of the lens, which is written on the top of the figure. Okay, so there is a lot of work to do, and so let me finish. I hope I convey the point that the work at the interface between analytic and numerical relativity has been essential to detect the signals and also infer unique information. I presented first waveform models for eccentricity, with eccentricity until now for aligned spin black holes. But here, what is absolutely important is to include also the spin precession, not just eccentricity, to be able to properly identify the binary systems on generic orbits and also draw robust conclusion on the eccentricity or a possible eccentricity subpopulation. So far, the systematics due to modeling have not affected the results mainly because the statistical error is still quite large for the events we have observed so far for LIGO and Virgo, but the problem will not be the same for upcoming runs and future detectors, where this comprehensive analysis using the state-of-the-art waveform models are shown clearly sign of biases, in particular for large spins and large mass ratios and spin precession. And so finally, this is what I was saying in my last slide, we need to improve the waveform. And the plot on the right shows you the upper panel, the cumulative detections with all the detectors in the future, with an SNR larger than 10. You can see how many we will detect, also including Lisa with massive binary black holes. And the panel on the bottom is actually how much SNR the very first event, 150914, will have in the future if we continue to observe events of that kind. So I want to thank my group with these pictures and also the agencies, and thank you for your attention. Thank you, and sorry for taking a little bit more time.
Thank you, Alessandra, for this very interesting talk. And This progress is really exciting. Any questions?
Yes, I have a question.
Yes, I
Okay.
can go back also to share. I didn't want to go out, but somewhat, just 1 second, maybe I can reshare again in case I need to.
Okay, I'll start, and I
Yeah, why
think there
don't
was
you
another
start?
question as well. So thank you, Alessandra, for the talk. And I would like to ask about the duration of events. So we can talk about duration both in absolute time, in seconds, and in the number of revolutions that we see. I remember that the first event was a fraction of a second and maybe a few revolutions. And then later there was, I remember, a longer event with neutron stars that was tens of seconds, I think. And as we extend the sensitivity, we expect to have longer and longer events, maybe even allowing us to go back from the merger back in time up to where post-Newtonian theory is valid. So my question is if you can relate to this statistics or the current status of event durations.
Yeah, indeed, you know, because the duration of the signal is mainly dictated by the bandwidth of the detector. And so at the moment, the lowest frequency is around 20 Hertz. So in order to have a longer signal, either you reduce the total mass, like you mentioned, the binary neutron star had 3,000 cycles, if I remember correctly, maybe starting from 25 or 30 Hertz. And so in the future, as we move the frequency toward lower frequency, for example, with Einstein telescope and Cosmic Explorer, if I remember correctly, people pointed out that a binary neutron star could be seen for several hours, if not for a day, sweeping in band. So, and for LISA, as I was mentioning, the binary neutron star, the massive black holes will be in band for months or an entire year. So then, you know, you can go in the low frequency part, and there, indeed, you know, templates based on post-Newtonian theory should be more and more accurate. So I don't know if I address your question, but indeed, you know, there will be a lot of variability in the future.
I think what you're telling me is that the duration of the event is not limited by sensitivity, but it's limited by frequency. So the fact that we improve the sensitivity, but we don't have a wider frequency, means that so far we don't have much longer events.
Yes, I would say so. Although, of course, you know, what matters to really detect the event is also the signal-to-noise ratio, right? So you could also have, I mean, if your detector is not very sensitive, of course you don't detect it. But yes, the frequency is very important, the bandwidth of the detector. One thing I wanted also to mention, so I said that if the total mass is small, you have many more cycles, but also starting from the same frequency, if the mass ratio is large, you also have many, many cycles. Now, if you think about the MRIs, you have many cycles because the black hole, the small black hole has a mass much smaller than one of the big black hole, and so it makes many, many, many cycles.
But this is not observed yet.
No, this will be actually, LISA, are these tracks that you see here, the different harmonics for an event like, yeah. But for example, you know, I mentioned for Einstein telescope Cosmic Explorer, for example, this mass ratio 10 to the 3 that you see in the bottom right, these are not extreme mass ratio inspired because the mass ratio is not 10 to the 5, 10 to the 6, but still, this will be very interesting. They will last for a very long time in the bandwidth because of the mass ratio.
Okay, thank you.
You're welcome.
I may have another question. Hi, thanks for the talk. I'm a PhD student at Weizmann Institute, and I was wondering, you were showing the comparison of the numerical relativity, IMR phenomics PHM, and the surrogate model, and you said that you made the best match for the time and for the phase. and then you compare it how far away are the models. But what if you also did the best match for other parameters? Like, for example, if you change a little bit the masses or the spins, then you can have a bigger match between the numerical relativity and IMR phenomenon PHM. I'll explain why I'm asking. Like, let's say I'm building a template bank from IMR phenomenon PHM. I don't care that there is a bias in recovering the spin, but I do care about covering all the parameter space, about detecting and finding a close match to all possible parameters. Will this be achievable?
Yes, thank you for the question. In fact, there are two different problems here. I want to go back to this slide I had. So there is a detection problem and there is the inference problem. So when you detect a signal, you don't need to measure the parameter well. And in fact, you do allow the parameter to change. And if you consider the template bank for 02, 03, or 04, was a template bank with only 4 parameters, the 2 masses and the spin components along the direction perpendicular to the orbital plane. So it was not even a precessing template bank, a precessing waveform that was used. And this template bank, even if has not precession effects, otherwise will be higher dimensional, is still able to recover quite well, although of course, you will have a drop in the signal to noise ratio if you have a highly precessing object and you try to detect it with a aligned spin template bank. So I was mainly focusing, so again, just to conclude, for detection, absolutely agree with you, you can change the parameters. You don't care that you get the wrong parameter from the template bank. But what you care is that after the detection, you run this inference analysis, with Markov-Chain Monte Carlo, nested sampling, or machine learning codes, and there you do care about the recovery of the parameters. So and there, if you are now changing the parameters in order to get a good match by minimizing, maximizing the likelihood, etc., then that's a problem, because this is what I was showing in this plot, where you have, this nice waveform. Where is it? Sorry. Yeah, so this problem here, where now I'm interested not in the detection, but in recovering the parameter. My signal is SUBNR V5 PHM. So I don't change the parameter and I get a difference with a green. Now I reduce the difference by, changing the parameters. So I do my Bayesian analysis so that I get the best parameters that fit SUBNR V5. But then I get a bias in the total mass 3%, in the mass ratio 6%, and in KP 13%. So then I get my Poisson distribution, which are away from the true values, which is what I was showing in these plots here, which is a problem.
Yes, sure. But my question was, like, for example, I'm designing a search, and I want to test whether my search covers the actual physical reality or not. Will I be able to, like, what would be my completeness? Will I be able to detect 100% of signals which will come to me from the nature? And to test this completeness, I need to model some population and then to run my search on this simulated population. So can I say that what I can model with IMR phenomenon PHM is representative of the reality, that it will sort of cover the possible shapes?
Yes, I see what you mean. I would say, I would say for quasi-circular orbits, I would say that IMR phenomenon X PHM should be a good representation, because even for these cases where you see a large, difference in the recovery of the parameter, I think you will still be able to detect the signal, because I think it has enough, it allows to have enough shapes, as you said, to recover actually the shapes of SUBNR V5 PHM. But of course, and I think this is perhaps what you have already done, you can test this by doing an injection study. So you take your template bank of IMR phenom XPHM, and then you do an injection study injecting SEO-BNR-V5 PHM, and try to understand what's the effectiveness of the template bank in recovering SEO-BNR, and you can compare that when you inject IMR phenom X. You see what I mean? So that you can,
Yes.
yeah, you could do that to understand how good is the template bank in recovering all these different shapes of these two waveform models.
Thank you.
You're welcome.
Okay, we're quite over time, but does anybody want to ask the last question? Or should we conclude? Okay, so let's thank Alessandra once more for a very interesting talk.
Yeah, thank you very much. And I hope to see you some other place. Bye. Bye-bye.
Bye.